Now we are going to an interesting result because we see that jpx and j minus px are linearly independent, but when n is a positive integer, j minus nx and jnx are linearly dependent. So the two independent solutions of Bessel equations may be taken as one is jnx. We know what is jnx. We know that jnx, and the other is yn of x, ynx. This ynx is given by cos pi jnx, cos pi into jnx minus j minus nx on, so cos, not a cos pi, simply cos n pi jnx minus j minus nx divided by sin n pi for all values of n, for all n. For all n means, here we classify this into two cases. One is n is an integer and the other case is n is not an integer. Why? Because we see when n is an integer, more precisely it is positive integer, we got two linear dependent solutions. But here we are discussing the linearly independent solutions. One is jnx and the other is ynx. Jnx and ynx are linearly independent, and ynx is given as cos n pi jnx minus j minus nx all by sin n pi true for every n. So we are going to the proof case first. When n is not an integer. N is not an integer. This is our first case. When n is not an integer, then we know that this ynx from this equation. Ynx is a combination of jnx and j minus nx. And we know that when n is not an integer, j minus nx and jnx are linearly independent. Okay. When n is not an integer, we say that when p is not an integer, j minus px and jpx are linearly independent. So when n is not an integer, j minus nx and jnx are not linearly dependent, means they are linearly independent. So since j minus nx and jnx are linearly independent, therefore this jnx and ynx are also linearly independent. Jnx and j minus nx are linearly independent. Therefore, jnx and the linear combination of this jnx, this is nothing but the linear combination of jnx and j minus nx. Cos n pi by sin n pi into this one, minus 1 by sin n pi into that one. When n is not an integer, it's a linear combination of jnx and j minus nx. So, this jnx and ynx are linearly independent. So, the first case is OR. So, when n is an integer, n is not an integer, the result is immediate. Okay, jnx, j minus nx, when n is not an integer, these are linearly independent. But ynx is a linear combination of these two. Since these are linearly independent, the linear combination is also linearly independent. Therefore, jnx and the linear combination of these two, jnx and j minus nx are also linearly independent. So, that is what we require here. Second case, n is an integer. When n is an integer, may be positive, negative or 0. When n is an integer, what is cos n pi? When n is an integer, cos n pi equals minus 1 power n. Okay. And what is sin n pi? We know that sin n pi equals 0. For any integer value n, cos n pi is minus 1 power n, sin n pi is 0. Also we know that when n is an integer, j minus nx equals minus 1 power n jnx. This happens when n is an integer. Okay. Apply all these values to here. So what you get here, y n x equals, when cos n pi minus 1 power n, j n x minus j minus x is again minus 1 power n j n x all divided by sin n pi 0. Okay. So it's a y n x is 0 by 0 form. 0 by 0 form means it's an indeterminate form. So when this indeterminate comes, then now we goes to L'Hospital's rule. Okay. So by L'Hospital's rule, before going to this L'Hospital's rule, since y n x equals 0 by y n x is in 0 by 0 form when n is an integer, then we write this y n x is in this way. Y n x equals limit p goes to infinity y px. So p goes to n. Limit p goes to n y p of x. Okay. Limit p goes to n y p of x means that is equals limit p goes to n y p. So it is cos p pi jpx, cos p pi jpx minus j minus px all divided by sin p pi. Okay. But we know that when p equals n, limit p goes to infinity means p goes to n. So p equals n. When p goes to n, what is this y p of n of x? That's then this right side is 0 by 0. So by L'Hospital's rule, by L'Hospital's or L'Hospital's rule, what do you get? It is some derivative of, you can del by del p of numerator means del by del p of cos p pi into jpx minus j minus px all divided by del p of sin p pi. So this is for, and all of these cases are for p equals n. Okay. Which equals derivative of cos p pi into jpx by using product rule. Cos p pi minus sin p pi into pi. So it is minus pi sin p pi into jpx. Okay, into jpx plus cos p pi into del by del p of jpx. That is, this can be rewrite as, that is same as minus pi sin p pi jpx plus cos p pi into del by del p of jpx minus del by del p of j minus px all divided by del p of sin p pi, that is pi cos p pi. This is for p equals n. P equals n. Okay. So when p equals n, n is an integer. So what I get? The first time this goes to 0. Sin n pi. We know that when n is an integer, sin n pi goes to 0. When p equals n, this is first term minus pi sin n pi, that is 0, plus cos n pi into del by del p of jpx. Del by del p of jpx minus del by del p of j minus px all divided by pi into cos p pi means cos n pi pi into minus 1 power n. Okay, that means after supplying the value of p equals n, you have this value, that is pi n x equals, this is cos n pi into del by del p of jpx minus del by del p of j minus px all divided by pi into cos n pi. Agree? So what is cos n pi? Cos n pi we know that cos n pi when n is an integer it is minus 1 to the power. This cos n pi is also minus 1 to the power. Okay. So that means this ynx equals 1 by pi into minus 1 power and cancelling each other. Why? Because there's a minus. This can be minus 1 power 2n. Minus of 1. 1 can be rewritten as minus 1 power 2n. Put minus 1 power and goes outside. All of this minus 1 power and are cancelling each other. Or then you have 1 by pi into del p of jpx minus 1 power n into del p of j minus px. Okay, here this minus 1 power 2n minus of, there is a 1 can be rewritten as minus 1 power 2n and the minus 1 power n commonly goes outside, then cancelling each other. Here minus 1 power n remains. So it is ynx equals 1 by pi del p of jpx minus 1 power n del p of j minus px when for p equals n again. Okay. So that means that is our first result. That is again I rewrite as ynx equals 1 by pi. It is 1 by pi del p of jpx minus 1 to the power n del p of j minus px for p equals n. So this is our one of the results. This is ynx. Okay. But we know that what is jpx? Jpx and j minus px are the solutions of, they are the linear independent solutions of the Bessel equation x square y double prime plus xy prime plus x square minus p square y equals 0. That means this equation satisfied by this jpx and j minus px, so we get x square d square by dx square by dx square of jpx plus x d by dx of jpx plus x square minus p square into y means jpx equals 0. Okay. Again it satisfies j minus px, that is x square d square by dx square of j minus px plus x into d by dx of j minus px plus x square minus p square into j minus p of x equals 0. Okay, so you can mark it as some of the equations. Suppose it is a and b. Then differentiate this a and b with respect to p. Differentiate this a and b. Differentiate equation a and equation b with respect to p. Comment to it. What do you get? If you differentiating that function, that equations with respect to p, then that is obtained as x square into d square by dx square of del p of jpx plus x into d by dx of del p of jp plus x square minus p square into del p of jp. Again by using product rule here, it is minus 2p into jp equals 0. Okay, so if you are differentiating that one, then you have a becomes x square into, yes, it is d square by dx square del p of jp plus x into d by dx of del by del p of jp plus x square minus p square. You can apply the product rule, del by del p of jp. Now minus 2p into jp equals 0. Similarly, you can derive or differentiate this equation b with respect to p. You have this one, that is x square, again d square by dx square of del by del p into j minus p plus x into d by dx of del by del p of j minus p plus x square minus p square into del by del p of j minus p minus 2p j minus p equals 0. Then you can find this is equation C and D. And you multiplied this equation D by minus 1 power p and subtracting that equation from C. That is, our next step is equation C minus 1 power p into D. Equation D. First we multiplied equation D with the minus 1 power p and subtracting the obtained equation from C. Then what I get? It is here, this is common, so you have x square into d square by dx square of del by del p, that is del by del p jp minus 1 power n into minus 1 power p into del by del p of j minus p. Okay. Again from here, plus x into d by dx of, again, del by del p of jp minus 1 power p del by del p of j minus p. Plus, again from here, it is x square minus p square into del by del p of jp minus 1 to the power p del by del p of j minus p. And minus 2p into jp minus 2p into j minus p, that is minus 2p into, it is jp minus 1 power p j minus p equals 0. C minus 1 power p d equals this one. Okay. Now put a p equals n. Now put a p is only our choice. Put a p equals n. What do you get? When p equals n, this becomes, it is x square into, again, d square by dx square of del by del p of jp. Listen, it is del by del p of jpx minus 1 power n del by del p of j minus px. What is actually this one when p equals n? It is 1 by pi into ynx. Using this argument. Del by del p of jpx minus 1 power n del by del p of j minus px when p equals n is pi ynx. So when put a p equals n, this equation becomes x square into pi ynx plus x square into, this becomes x square into d square by dx square of pi ynx. Okay. Pi ynx plus, here it is again x into d by dx of, what is again this one? Del by del p of p jp minus 1 power n when p equals n. Del by del p of j minus p is pi ynx. So it is pi ynx plus x square minus n square, not y p square. Why? Because we choose p is n. This is again pi ynx pi y nx minus 2p into jp minus means 2p into jp means jnx minus 1 power n into j minus nx equals 0. Okay. But when n is an integer, we know that j nx is same as minus 1 power n j minus nx. So the last term vanishing. So this term vanishes. Why? Because when n is an integer, we know that j minus nx is minus 1 power n jnx. Okay. So this reduces to x square when pi is commonly outside. Pi into all of these terms equals 0. Pi differs from 0. So there is only possibility this x square into d square y by dx square of y n x. D square y by dx square of y n x means y2 dash or yn2 dash. What? This pi is commonly taken outside. X square into d square by dx square of yn plus x into d by dx of yn plus x square minus n square into yn equals 0. Okay. Pi differs from 0. Pi strictly differs from 0. So only possibility the term inside this bracket should be 0. The term inside that bracket can be rearranged as, what is that one? It is x square double prime means x square yn double prime plus x into yn prime plus x square minus n square into yn equals 0. This means this yn is nothing but a solution of the given Bessel equation, that is x square y2 dash or y prime means this means yn be a solution of this x square y double prime plus xy prime plus x square minus n square into y equals 0. Okay, that means yn is a required solution. So here ynx is also a solution, and jnx when n is an integer, ynx is a solution, hence they are linearly independent. So the general solution of when n is an integer, the general solution of Bessel equation is y equals a into jnx plus b into ynx, where a and b are constants, where ynx is defined as cos n pi jnx minus j minus nx by sin n pi for all n.